Everyone, I'm Sebastian, and in this presentation I want to talk about a new hooking concept that we call dynamic hooks. And the key idea behind the hooking concept is to hide the changes, the control flow changes the hook tries to achieve with the non-control data, such that the hook becomes more difficult to detect. But before I talk about this hooking concept in more detail, let me briefly cover what hooks actually are and explain the limitations of current hooking mechanisms. So, to provide this malicious functionality, malware in general needs to intercept events within the system. Without event interception, malware couldn't provide simple functionality such as keylogging, file hiding, process hiding, etc. To intercept events, the malware essentially must divert the control flow of the system at runtime whenever the event that the malware is interested in occurs. And this is accomplished by installing hooks into the control flow of the code that handles the event. And so far, there have basically been two mechanisms for hooking. So on the one hand, we can either change the code that handles the event. So for instance, we can override existing instructions with a branch instruction such that the malware will be invoked whenever the code that is handling the event is actually executed. Alternatively, we can change a function pointer that is used by the code and point this function pointer to the malware, such that when the hook that handles the event invokes this function pointer, it will actually trigger the execution of the malware and not of the original function. The problem with both of these approaches is, however, that they can be generally easily detected in practice, and researchers have presented various mechanisms to do so. So while malware managed to hide itself, the hooks that the malware places present a weakness in the malware's design that are very good or that are suited for its detection. So the question arises, how can we actually evade existing hooking detection mechanisms, and how can we avoid this flaw? And to address this question, we took a look at existing hooking mechanisms, and we found, or hook detection mechanisms, and we found that they're generally based on the assumptions that an attacker can only modify persistent control data to install a hook. And persistent control data is essentially data that is permanently used by an application, such as a function pointer that resides on the heap. But an attacker cannot use transient control data, which is only valid in the current scope of the function, such as a return address on the stack, to leverage hooking, because this transient control data would vanish as soon as the function returns. So in the paper and in this presentation, we're going to show that this assumption is false, and then we can indeed use transient control data to create a reliable hooking mechanism and evade existing detection mechanisms. So with this background in mind, let's take a closer look at dynamic hooks and how they actually work. So the general idea behind dynamic hooks is that we will apply exploitation techniques to the problem of hooking. In particular, we will modify non-control data in such a way that this non-control data will trigger a vulnerability as soon as it's used. And through this vulnerability, we will change the control flow at runtime. And through this approach, we can actually achieve two things. So first of all, we can target transient control data. And since this data will trigger a vulnerability every time it's used, we can use this to perform actually or to implement a reliable hooking mechanism using transient control data. And secondly, there is no evident connection between the data we modify and the control flow change anymore, since we now modify normal data and no longer control data, which makes it a lot more difficult to actually detect those hooks. However, if we look at the approach, an initial problem seems to be that we need a vulnerability in every function that we want to hook. And this seems to be impractical at first glance. However, there is a very important difference between the vulnerabilities we can use for dynamic hooks and the vulnerabilities we usually face in traditional exploitation. So in particular, when we think about a traditional exploit, we usually face the problem that we are an external attacker and we try to find some sort of input that triggers a vulnerability in the application. However, when it comes to hooking, we already control the application, and therefore we have a very different attacker model. So first of all, we are not affected by most protection mechanisms, such as RSLR, for instance, because if you already control the application, we already know all the addresses in the application. Secondly, we can not only target external functions, but also internal functions. That is, we can manipulate internal data structures that usually couldn't be manipulated by an attacker and create new vulnerabilities that wouldn't occur during normal operation. And lastly, we can prepare our shellcode that we want to execute once we trigger the vulnerability in advance, which means We only need simple control flow modifying vulnerabilities. We don't need the capability to also load our code at the moment we trigger the exploit. And this is, of course, a much stronger attacker model than in a classical exploitation scenario. Let's take a look at a concrete example for dynamic hook. So what you see here is the list delete function as it's used in the Linux kernel. And for those of you who have ever done heap exploitation, the code will look really familiar. So essentially what we can do with this code is if we control the list head entry that is passed to the list delete function and we control the next and the pref pointer, we essentially have a write where what primitive. With the line that is highlighted here, we can actually perform a write at the address next +8 where we write the pref pointer to. And at the same time, we can write the address that next contains into the address that pref is pointing to. And if we now imagine that the code which handles a event that we want to hook calls the list delete function and that we can control the list head that is passed to this list delete function, we can use this write reward primitive to create a dynamic hook as follows. We will essentially point the pref pointer to the return address of the list delete function. We will point the next pointer to the hooking code that we want to invoke. And as soon as this modified list entry, this malicious list entry, is used by the list delete function, we will override the return address with the location of our hook, and as soon as the function returns, our hook will be invoked, or our hook code will be invoked instead of the traditional control flow. So this example nicely demonstrates the advantages I tried to convey before, because what we see here is we are not restricted by existing protection mechanisms. In addition, we create a new functionality by manipulating a list entry that usually cannot be manipulated by a user, and therefore the list delete function becomes vulnerable and we can use that to achieve our control flow change. And at the same time, we can do this with a simple 8-byte write. We don't need to load our code. All that we need to do is to override control data, such as a return address. In principle, any vulnerability can be used to implement a dynamic hook. In the paper, however, we primarily focus on 8-byte writes since we target 64-bit systems. And an 8-byte write on the assembly level is essentially just a move instruction that moves a value stored in one register to the location pointed to by another register. So in this case, we move the value stored in RBX into the location pointed to by RAX. In general, there exist two types of dynamic hooks. There exist dynamic control hooks, as we just saw in the example, which allow us to change the control flow. But we can also use the same primitive to create data hooks which just perform data-only attacks. Consider, for instance, that we point the pref pointer that we saw in the last example to the effective user ID of a process on Linux, and we point the next pointer to an address that ends with 4 0 bytes. In this case, as soon as we delete this entry with the list delete function, what will happen is that we override the effective user ID of the process with zeros, meaning that we will evaluate its privileges to root. So we can use this, for instance, for a backdoor to demonstrate poor data-only attacks. To find dynamic hooks, we implemented a prototype that leverages a two-stage approach. So first of all, we want to find any path that could potentially be used for a dynamic hook. And for this purpose, we use program slicing. Essentially, what we are going to do is we extract every move instruction, every 8-byte move instruction from the binary, and we try to understand where the source and the destination values that are used in the last move originate from. And for this purpose, we perform a backwards breadth first search and just follow the information flow in the backwards direction through the program such that we see where it originates from. And if the source value and the destination value originate from a global variable, meaning we know exactly where it comes from and we can control this final move instruction, then we consider this path to be suited for a dynamic hook. And a global variable in this context essentially means that the last move instruction, or where the source and the destination value originate from, is a memory location pointed to by the GS segment, since the GS segment contains global variables in the case of Linux and Windows in the case of 64-bit systems. And our current implementation is based on IDA Pro in this case. Once we have extracted a potential path that we can use for a dynamic hook, we use symbolic execution to check whether the path is satisfiable. And for this purpose, we first transform the extracted path into the VEX intermediate representation using PyVex. We then map the VEX statements into set3 expressions and execute the code symbolically. And in the process, we check whether the conditional branches are satisfiable, and we generate detailed information about the dynamic hook. For instance, which memory location we need to update to actually perform the last move, and which memory locations we need to update to actually pass the jumps. We tested this prototype based on Linux and Windows. We used the Linux and the Windows kernel, to be precise. This is the Linux 3.8 64-bit kernel and the Windows 7 Service Pack 1 64-bit kernel. And what you see in this table here are, first of all, the instructions that both of those binaries contain, and next to it, all the 8-byte move instructions contained within this binary. And then we applied our slicer to all of those move instructions and tried to find paths or slices that could be used for dynamic hook. And in the case of Linux, we found 1,753 slices that can potentially be used for dynamic hook. In the case of Windows, we found 5,450 slices. And these slices were then fed to the symbolic execution engine, which led to 566 paths that are satisfiable in the case of Linux, and 379 paths that are satisfiable in the case of Windows. So what I have to mention here, what is important, our current prototype faces some limitations. So first of all, our program slicer currently doesn't support a memory model, meaning that when the information flow stores a value temporarily somewhere in memory, which is not pointed to by the GS segment, we cannot follow this information flow, and so we ignore the path. And during our experiments, we ignored 80,000 paths due to this restriction. And our symbolic execution engine, since we use the VEX intermediate representation, and the VEX intermediate representation doesn't support the whole x86 instruction set, especially privileged instructions are a problem there, and they're used often within the kernel, we couldn't check roughly 6,000 of those slices we extracted during our experiments. So this shows that the real number of paths that can probably be used for dynamic hooks is much larger than the path that we found in our experiments. However, even with the few paths we found in the experiments, we can already perform real-world exploitation and real-world hooking. And to demonstrate this, we created 3 prototypes. So the first prototype is a control hook for Linux that allows us to intercept arbitrary system calls, which is a typical hooking functionality. The second hook that we implemented is a backdoor for Linux. It essentially levers the mechanism that I described before to evaluate the privileges of a process to root. And last but not least, we implemented a control hook for Windows, which is capable of intercepting arbitrary process terminations. The details of all the prototypes are in the paper, or if you're interested, you can also talk to me or one of my colleagues after the talk. So dynamic hooks, of course, also have some limitations. So first of all, the vulnerability that we use for the dynamic hook may place some restrictions on the hook itself. So as we saw in our example at the beginning, we are not only writing the next pointer into the address pointed by pref, but we're also writing pref into the address pointed by next plus 8, as you can see here on the left side. So we essentially write into our shellcode. And we have to somehow mitigate this problem, and generally we have to find a location for our hook code that is writable and executable. So this is a typical restriction that could be placed on a dynamic hook based on the vulnerability that you're exploiting. A second problem I haven't talked about so far is coverage. So how many times is the hook actually triggered? Is it triggered for every event or just in specific cases? And our prototype can currently not determine this. So if we extract a path, we don't know if its coverage is full, meaning that it's invoked on every event, or if it's just invoked sometimes. And in general, we of course want full coverage for hook because we want to accept every event. But in the case of backdoors, it can also be beneficial if you just have a hook that is triggered in very specific conditions, right? Exactly then when we want to trigger the backdoor. So coverage is not necessarily a disadvantage, but we cannot at the moment automatically evaluate it. And secondly, what about side effects? So if you modify stuff in the kernel, this can go very badly if the data that we modify is used somewhere else. And in an ideal scenario, the data that we modify is only used within the hook that we leverage. And as coverage, we cannot at the moment automatically determine whether this is the case or not. But as our prototypes have shown, we can create really hooks where the data is just used in a specific control path and can use this for reliable diverting the control flow at runtime. So to conclude, dynamic hooks enable us to await existing detection mechanisms because we target transient control data instead of persistent control data. Dynamic hooks are more powerful than existing hooking mechanisms since we can perform control flow attacks, but we can also perform data-only attacks. And last but not least, dynamic hooks are difficult to detect because we change non-control data. Non-control data happens to change very often. So it's difficult to verify compared to control data, which doesn't change frequently. There are also a few disadvantages, of course. So first of all, this hooking form is naturally more complex than traditional hooks because we leverage vulnerabilities and exploits. And in traditional hooking, we just modify a function pointer or we modify code. And dynamic hooks are more fragile than traditional hooks because we update data, and this data may be used in different places within the kernel. But as I said before, we have shown that we can use this mechanism despite of this restriction to create reliable hooks. I thank you very much for your attention, and if you have any questions, I would be happy to answer them.
If you have questions, state your name and affiliation.
Raphael, so one quick question is why VEX, and what other sort of intermediate representations you tested, and what are sort of the pros and cons that led you to decide to use VEX? It seems like an interesting choice. I was just wondering what led you there, as opposed to like BAP or I guess Bill.
We tested various different languages. I don't know, like I don't have the languages all in my head. We ended up with VEX because it was the only thing that worked in the end. So we had not really another choice for language when we implemented
so for you it was the only thing? Okay.
Exactly. We had just practical problems with all of them. So if you're interested in, I would recommend you talk to Behrad, who implemented the stuff on VEX. He's right there, and he can exactly tell you which languages we tried and where the problems were. Sorry.
Any other questions? So the side effects was something that immediately sort of struck me as sort of an inherent limitation of this. And it sounds like you don't have really the ability to measure that quantitatively, but do you have a feeling of how common certain paths have side effects versus not side effects, given the experience in developing the vulnerability, the exploits?
That's a really good and a really difficult question. So the problem is, even if data is used in multiple locations within the kernel, it doesn't necessarily mean that we cannot use this for a reliable hook, because there may be branches that we can manipulate such that the data is no longer used within this other path. So it really depends on a human expert to look at the paths. So we found various paths that didn't seem to be exploitable, but when you spend some time with them, then you find a way to actually make it work. So I can't give a measure here, really. It's a manual process.
All right. If we don't have any questions, let's thank the speaker again.